What's up, everybody? It's Miles here from bootcamp.com, and today we're going to be going over ventilation and dead space. So let's recall that we have very thick airways, and in contrast, we have very thin alveoli. And can you remember what the epithelium was called of the airways? That's right, it was called pseudostratified columnar epithelium with goblet cells. Now remember that the airway epithelium is so thick that air cannot pass through it. It cannot pass through. Whereas the alveolar membrane, which is made up mostly of type 1 pneumocytes, is very thin, and so it does allow gas to pass through it. And where air cannot pass through, we call that a non-gas exchanging surface, and when air can pass through, we call that a gas exchanging surface. In the air that occupies the airways, which are non-gas exchanging surfaces, we call this volume of air dead space. And the air that occupies the alveoli, we don't call that dead space because that air is in contact with surfaces that can undergo gas exchange. And so the air that exists in these thick airways that is not undergoing gas exchange, that's normal. That's normal dead space. And we call normal or naturally occurring dead space anatomical dead space because it's found in all of us based off normal anatomy of the airways and bronchi and trachea that naturally do not have gas exchanging surfaces. And recall from our first video that all of these anatomical regions I just mentioned that do not participate in gas exchange is called the conducting zone. And so the anatomical dead space is really just the volume of air that occupies the conducting zone. So moving on, let's recall that in order for gas exchange to occur, there has to be an exchange of gas between the respiratory system and the blood. So let's just draw in a blood vessel that has a close relation to the alveoli here. So like we just said, gas exchanges from the alveoli into the blood and from the blood to the alveoli, and there has to be a close proximity of the blood to the alveoli. But what would occur if we had, let's say, a blockage in the blood vessels, such as an embolus or a clot? Well, in this case, even though the alveolar membrane is still intact, there is no blood for the alveoli to exchange gas with. So now we say that the alveoli actually isn't a gas exchanging surface anymore. When the alveoli doesn't have blood to exchange gas with anymore, now we classify it as dead space. However, this kind of dead space is not normal, it's not natural, and it's not found in healthy individuals like in the case of anatomical dead space. This kind of dead space is pathological, and we call this dead space alveolar dead space. So if we take an individual and we want to know what is their total dead space, and let's say we don't know if they're healthy or diseased, so we don't know if they have any alveolar dead space or not, we just want to know what is their total dead space. Well, in this case, physiologists like to try to find something called the physiologic dead space. And what this dead space is the total dead space taking into account the normal anatomical dead space and potentially if the person has any alveolar dead space. So this dead space is essentially the sum of both of those dead spaces together. And fortunately, yet kind of unfortunately for us physiology students, there is an equation that was developed. It's called Bohr's equation. It's right here, and it determines what the physiologic dead space is. And so the equation is the volume of the physiological dead space is equal to the tidal volume multiplied by a ratio. In the numerator, we have the arterial partial pressure of CO2 minus the expired partial pressure of CO2 divided by, again, the arterial partial pressure of CO2. And so there's a trick that some students like to use to remember this equation. However, you still need to know the structure of the equation, which is a variable multiplied by a ratio. And in the numerator of the ratio is a subtraction divided by a variable. And so the trick is taco, paco, pico, paco. You pretty much just have to say it a few times to memorize it. But the taco is for the tidal volume. The paco is for the arterial partial pressure of CO2. The pico is for the expired partial pressure of CO2. And then the final paco is for, again, the partial pressure of arterial CO2. And there's really not a lot of questions that require you to use this equation to calculate physiological dead space. It's much more important to just understand the concept of physiological dead space. And I think that even the step one is kind of moving away from using big equations like this. However, I do know that there are a couple practice questions out there that require you to use this equation, so we did include it in the video. So moving on, like we said, the concept of physiological dead space is that it's the sum of alveolar dead space and anatomical dead space. So in a healthy individual with healthy lungs, the physiological dead space should be equal to the anatomical dead space because we're not adding any alveolar dead space to the anatomical dead space. The alveolar dead space is going to be 0. However, in a diseased lung, in diseased individuals, the physiological dead space is going to be greater than the anatomical dead space because recall we just said physiological dead space is anatomical plus alveolar, and that's obviously going to be greater than anatomical alone if alveolar is not 0. Okay, so now that we've discussed dead space, we can start to talk about ventilation, and we'll start with minute ventilation. So minute ventilation is the amount of air that enters the lung each minute. And recall from our previous video that we said the amount of air that enters the lung each breath is our tidal volume. So if we multiply the tidal volume, which is our volume per breath, multiplied by our respiratory rate, which is the amount of breaths we take per minute, then we're going to calculate how much volume we're bringing into the lungs per minute. Let's say that our tidal volume is 500 milliliters and our respiratory rate is 10 breaths per minute. Then that means we're going to be bringing 5,000 milliliters of air into our lungs every minute. All right, and let's finish off by talking about alveolar ventilation. The alveolar ventilation is the amount of air entering the alveoli each minute. And like we just said, the amount of air entering the lungs each minute is the tidal volume. But of the tidal volume, only a portion of that actually gets deep down into the alveoli. The rest of the air on top of that stays in the conducting zone and so is considered dead space. And so to calculate alveolar ventilation, we need to take our tidal volume and we need to subtract dead space from that. And so as an example, I have the normal values that you'll usually see in questions in the top right over here. So we would have our tidal volume, which is 500 milliliters. We would subtract our dead space volume, which is usually about 150 milliliters. And then we would multiply that by our breathing rate. Let's say it's 10 breaths per minute. And so our alveolar ventilation would be 3,500 milliliters per minute. All right, and that's all we got for this video on ventilation and dead space.